Hello students, today in antenna arrays and application we will discuss about how to calculate field component for n element array. So already we have discussed about different types of array and what is the use, what is the need of arrays, and now we will discuss about in the array system if there are n elements, that is n may be any number of elements present, how to calculate the total field components for an array systems. So in this topic we are going to discuss about there are three different cases, that is for broadside array, n-side array, an array of elements with unequal amplitude and any phase. So but here we have to discuss about the two cases, that is broadside array, another one is n-side array. So before proceeding broadside array, n-side array, in this video we will discuss about how to calculate the field components for n elements. See the diagram. In this x-axis it says about there are n number of antenna elements present and the distance between each element is equal, that is d distance. It may be any value of lambda or lambda by 2, lambda by 4, 3 lambda by 4, lambda by 10, anything. So these are the antennas 1, 2, 3, 4 and it is called as array of point sources, and we consider that these point sources are isotropic point sources. It radiates equal power in all the directions. Now I am going to measure the field component from this point. This is called as a distance point P. So the total field component from the distance point is equal to the summation of individual field component radiated from the antenna systems in the array. So while measuring the total field component in the distance point, I am taking antenna number 1 as a reference with respect to the remaining. So while taking this as reference, and there is no phase introduced by this one, and the total phase angle from 1 to 2 will be e power j psi. So e power j psi is the phase difference between one another, that is due to the path difference, because while measuring the total field component from here, the path or the distance between the element to the location is different. Because of this there is a phase component, so phase angle will be appear. And this is the uniform array systems as well as linear array systems. And see here the total field component can be measured by this by taking the individual field, the summation of individual field component. So e naught e power 0 j psi, here there is no phase really because antenna number 1 is as reference. Then we have e naught e power j psi, e naught e power 2 j psi, 3 j psi, like that it will be going on. And this is the antenna field component of antenna 1, field of antenna 2 and field of antenna 3, it will be going on. And see here for all the elements I have given equal amount of power, that is E naught is the equal amount of field is transmitted because this is an uniform array we are dealing. So then the equation number from this we have to take the component factor is E naught and e power 0 is 1. So hence we are getting this equation number 1. So whereas psi is the total phase angle at the distance point is equal to beta d cos theta plus alpha, where alpha is progressive phase shift between the elements. That is how we are feeding the current component, whether is there any phase difference between the elements or there is no phase difference. That's all about alpha. So alpha is progressive phase shift between the elements. So next the e power j psi is the phase difference between the one another with respect to antenna 1, because antenna 1 is a reference element. So I am going to multiply e power j psi with the first equation, then this equation 2 will be like this. Then I am going to subtract equation number 2 from equation number 1. It will be et minus et e power j psi is equal to, this is equation number 1 minus equation number 2. Then from this to the common factor is et and of 1 minus e power j psi, that is equal to E naught, it's a common value here, and 1 minus e power j n psi. So I am going to simplify this expression and I am going to calculate what is the total power from the n element. So here we have the equation et is equal to E naught of 1 minus e power j n psi by 1 minus e power j psi. The e power term can be neglected or that can be replaced by the cosine terms. So here I can write e power j n psi can be written as e power j n psi by 2 into e power j n psi by 2. So if we multiply these two, we will get e power j n psi. And similarly in the denominator, e power j psi can be written as e power j psi by 2 into e power j psi by 2. And for I am going to take e power j n psi by 2 in the numerator as well as e power j psi by 2 in the denominator. So you will get e power j n psi by 2 of e power minus j n psi by 2. So see, if we multiply these two terms, we will get 1. Because the power will be subtracted, it will be 0, so e power 0 will be 1. So this is a simple modification, and we are getting this expression. Now this e power, within bracket we have e power j n psi by 2 minus e power minus j n psi by 2. This is nothing but sin n psi by 2. So it is like e power j theta is equal to e power j theta minus e power minus j theta by 2, that is sin theta, right? So we are going to replace these terms by sin n psi by 2 by sin psi by 2, and here we have to simplify these two expressions. That we have the total power is equal to a naught into e power j of n minus 1 psi by 2, and this numerator denominator will become sin n psi by 2, the numerator will become sin psi by 2. So that is equal to e naught of sin n psi by 2 by sin psi by 2. Then I have taken this e power j pi, because pi is equal to n minus 1 psi by 2 from this expression. So e power j pi can be written as cos pi plus j sin pi. This also can be written as e naught of sin n psi by 2 by sin psi by 2. It is the total far field component. And in this case, the phase angle pi can be eliminated. That is, this can be eliminated in order to get maximum power. So if you put pi is equal to 0 here, cos 0 plus j sin 0. So we will have sin 0, it will be 0, and cos 0, it will be 1. So the terms can be the total cos pi plus j sin pi can be replaced by 1. So we have this equation number 7. And if we divide total power by individual power, it becomes sin n psi by 2 by sin psi by 2. It is called as antenna array factor. Next, when this total power will be the maximum value, when the total power, that is ET, will become maximum value, if there is no phase angle, that is psi is equal to 0 from the distance point, then this becomes maximum value. So for calculating maximum field component, I am going to substitute psi is equal to 0 in this numerator as well denominator. But if it put psi is equal to 0 here, sin 0 is 0, and by sin 0 is also 0. 0 by 0 will become indeterminate. So we have to apply L'Hospital rule. So L'Hospital rule is what? We are going to differentiate numerator as well as denominator, and then we have to substitute the limit psi is equal to 0. So this is the equation. So while differentiating, I am getting n by 2 cos n psi by 2 by 1 by 2 cos psi by 2. Now I am going to substitute psi is equal to 0 here. So it will be cos 0 by cos 0, it will be 1 by 1. So we are getting the value of n by 2 by 1 by 2. So while taking this 2 will be cancelled, then we have E naught into n. So this is the total maximum total field component from the distance point, right? Okay, so how to calculate normalized value? Normalized field is equal to what is the total field by what is the maximum total field. So ET by ET max. ET we know E naught into sin n psi by 2 by sin psi by 2 by what is ET max? E naught into n. So the E naught will be cancelled. So we have normalized field component is equal to sin n psi by 2 by n sin psi by 2. So equation number 10, it is the normalized field component for n element array. So this is applicable for uniform as well as linear array. So with this we will complete this total field calculations. Thank you.